Next up, we have Dr. Eiling Zhang, who is a postdoctoral researcher at the University of California, Irvine. Her background is in hydrologic modeling, and she's currently working on integrating hydrologic and malaria modeling. Let's please give a hand to Eiling.
Hi, everyone. Good morning. Today, I will talk about our work on integrating hydrologic and malaria modeling to optimize agricultural practices in Western Kenya. This work is a joint effort between UCI Public Health and Center for Hydrometeorology and Remote Sensing. Okay. So in sub-Saharan Africa, many people struggle with food shortage, and this problem is getting worse because a majority of farmers practice rain-fed agriculture, and this is becoming less reliable because of the extreme weather events such as floods and droughts. So to improve the food security, irrigation projects such as dams and canals have been built. While these projects may bring economic benefit, they can also increase the risk of malaria by creating more places for mosquitoes to breed. Therefore, it's important to understand how different agricultural practices may affect malaria so that we can come up with mitigating strategies to limit its impact. So in our study area, we focus on Oluch irrigation scheme in Homa Bay County in Kenya. And this project was launched in 2007 to improve the livelihood of smallholders farmers. And this project involves channeling water from a watch Tende River into our project area. And the photos on the right shows the storage reservoir and the canals that distribute irrigation water within the farms. So although the irrigation infrastructures have been completed a few years ago, the irrigation is still a new concept in this project area. Only half of the total land is being currently irrigated, and most of the water meant to irrigate farms have been used for domestic purposes. And in addition, the majority of the farmers continue to practice rain-fed agriculture and grow mainly maize and beans. So to help the farmers achieve food security and at the same time also produce surplus for additional income, the county government has started to promote the utilization of irrigation water and diversification into rice and cash crops, such as vegetables and fruits. So in this context, we developed a few possible future agricultural practices and hope to answer the following research questions. Firstly, how does the increasing irrigation coverage affect the availability and characteristics of potential lava habitats? Secondly, how do different cropping practices affect malaria transmission intensity? And lastly, what is the effectiveness of irrigation strategies in mitigating malaria risk? To address this question, we developed a hydrology integrated malaria modeling framework. First, to model the effect of cropping practices and irrigation, we use a hydrologic model that allows us to simulate the energy and water balances associated with the farmlands. We set up our model using remotely sensed data, incorporating information on topography, land cover, and soil type. The output of the model is surface soil saturation, which later we post-process to determine the locations of potential lava habitats. Next, in the second step, we classify the identified locations based on their habitat stability, and then integrate this data into the EMOD model. Building on our 10-year simulation period, we established the model domain in the EMOD, in EMOD, consisting of 225 nodes, with each node covers an area of 0.75 square kilometers. And this model domain includes both irrigated and non-irrigated study clusters, allowing us to use our field data for model calibration. And using the framework as mentioned in the last slide, we simulated daily habitat area for each node in the hydrologic model. And the habitat area is expressed as a fraction of the node area. In addition, we also leverage on our field data on lava density so that we can estimate the distribution of habitat lava capacity for temporary, semi-permanent, and permanent habitats in the dry and rainy seasons. And finally, we created additional habitat functions and parameters in the EMOD model that can integrate the calculated data, the external calculated data into the model. We also accounted for human and vector migrations. To model human movement, we use a radiation model. So this model only requires one main parameter, which identifies the initial fraction of travelers moving to another location. And other than that, the model relies on population distribution data to estimate the migration flux between different nodes. For vector migration, we performed a random walk simulation for mosquitoes starting from a single location. And we constructed the model using a daily flight distance of 1,040 meters and a daily survival rate of 0.8. And the simulation ran for 40 days, and we analyzed the displacement using a histogram to which we fit a Weibull distribution. So finally, based on this distribution, we were able to create a mosquito dispersal matrix. Okay, now let's look at our irrigation scenario designs, which requires an understanding of the local weather patterns and the cropping restrictions. So in this area, there are two main crop seasons. The first crop seasons experience long rains from March to May. And the second crop season coincides with short rains from November to December. And as flooding is frequent in this area, the farmland can be divided into 3 flood risk zones. For example, so each zone has its own suitable cropping practices. For example, in the area prone to long-term flooding, a combination of rice, paddy rice, and peas is recommended. And in the short-term flooded zone, vegetables cannot be grown during long rains. And in the dry zone, there are no cropping restrictions. So on this basis, a feasibility study by the local irrigation project agency has proposed crop recommendations for this area, which we later use for our own recommended crop scenario later. We developed a few model scenarios that can classify into 3 groups. In the first group, we created a baseline scenario with 50% irrigated land, which we compare it with an ideal scenario where the irrigation infrastructure is maximized. So namely, 100% of the land is irrigated. In the second group, assuming 100% irrigated land, we also investigated 3 different cropping practices. The first one is the recommended crop assignment by the irrigation project agency, which involves growing diverse crops based on the flood risk zones. The second one is economy-driven, whereby farmers only grow cash crops, such as kales and tomatoes. And the third scenario assumes farmers practice subsistence farming. So the farmers only grow stable crops, such as rice and maize. Finally, building on the recommended crop assignment, we also look at 3 different irrigation strategies. The first one is flood irrigation. And the second one focuses on intermittent irrigation, specifically for rice. And the third one is water saving strategies, which combines intermittent irrigation for rice and drip irrigation for the other crops. Now, let's look at the results of our first group of scenarios. So in figure A on the left, increasing irrigation area from 50% to 100% increases the potential lava habitats by about 2 times. And we can see that the most additional lava habitats are permanent habitats. In figure B on the right, we found that the ratio of habitat area between the 2 scenarios is lower during the wet months. And this trend is also observed in other groups of scenarios. So, and implies that rainfall is the dominant controlling factor for lava habitats, regardless of agricultural practices. Here we show the habitat comparison for the second group of scenarios in figure A and the third group of scenarios in figure B. In figure A, we found that the habitat area in the cash crop dominant scenario is the highest compared to existing the recommended crop assignment scenario by about 10%. In figure B, using intermittent irrigation reduced the habitat area by about 23%, and water saving irrigations significantly reduced the habitat area by 53% compared to flood irrigation. So evidently, changing cropping practices does not affect habitat area by much, but efficient irrigations can have a much bigger impact. Next, we compare the spatial distribution of the annual average incidence rate among the 3 cropping practice scenarios. So from the map, we can see that the hydrology integrated EMOD has the ability to reflect the spatial heterogeneity of habitats and the resulting malaria transmission. We observe an expansion of malaria hotspots in the cash crop and staple crops compared to the recommended crop assignments. The associated increase in the incidence rates is about 20% and 15% respectively. We also found that the incidence rates decrease with the distance from the farmland. The incidence rate 5 kilometers away from the farmland is about 40% lower. Here we show the spatial distribution of annual average malaria incidence rates for the irrigation strategy scenarios. So as expected, we see a gradual reduction of the malaria hotspots when more efficient irrigations are applied. And the incidence rates decrease about 25% for the intermittent irrigation and 60% for the water-saving irrigation. In summary, based on the findings from the 3 scenario groups and considering the government's push to expand irrigation, the combination of recommended crop assignment and water-saving irrigation can be an appropriate approach. And interestingly, we also found that growing stable crops, because there's rice, right? So it requires a higher irrigation volume compared to the cash crop scenario. However, the resulting EIR and incidence rates are not higher as expected. So this suggests that the timing of the irrigation may play a more decisive role than the total irrigation quantity in determining transmission outcomes. Lastly, we also investigated the interaction between irrigation strategies and larviciding. And this figure shows how incidence rate changes with increasing larviciding coverage. And in the flood irrigation, we found that 57% of the area requires larviciding to maintain the baseline incidence rate. And with intermittent irrigation, it drops to 25%. And for the water-saving irrigation, no larviciding is required to maintain the baseline rate. So this shows that efficient irrigation strategies can be a viable supplement to larviciding in reducing malaria transmission by habitat reduction. In conclusion, we show how hydrologic modeling can be coupled with EMOD to simulate spatial temporal dynamics of lava habitats and malaria transmission. Secondly, we demonstrate the approach through a case study in which we found that both cropping practices and irrigation strategies can affect malaria, but more so the latter. And thirdly, the framework can be especially useful to model environmental modification as part of the lava source management to guide malaria control. Yeah, that's the end of my presentation. The work was supported by NIH, CHRS, and UCI Public Health. And here are the references. Thank you for your time.
Thank you so much for another great talk. Questions from the room? Yes, give me a moment to walk over to you.
Thank you so much for the great presentation and really great outputs. What I've been able to take home is the aspect of when we have intermittent, is it intermittent
yes.
irrigation?
Yes.
Water intermittent irrigation. That's when there is the reduced larviciding use, isn't it?
Yes. So intermittent irrigation, you don't irrigate the land for a very long time. You kind of like water the land for 7 days and let it dry for another 3 days.
Okay.
So that can significantly reduce the area. And that approach is specifically for rice lands.
Okay. Yeah. Okay. So I'm just curious also to understand further, maybe from what you've been able to do and the study that you've been able to carry out, what do you think would be, what is making the people, I don't know if the people around there are practicing that water intermittent irrigation, and if they're not practicing, why are they not practicing? And could you be also aware of the aspects that are affecting the larvae source control management approach of vector control, if you have any idea?
Okay, thank you for the question. So the first one, I think the farmers, they are just like lack of educations. They just practice what they have been used to. And in fact, like a lot of farmers, they don't actually make the irrigation, put the irrigation infrastructure into the good use. So they have to start practicing irrigation first, and then they will start to think how can make the irrigation water more efficient. And the secondly, for the larviciding, so I think, I know like right now, like in this area, they have started to do like the larviciding, like for lava source management. But I think from our presentation, I think like if we combine with the more efficient irrigation, then we probably can reduce some efforts of larviciding, or it can more maximize the effect of larviciding as well.
Okay, thank you.
Yeah.
Thank you so much. I'll come around for another question. Excuse me, Monica. Thank you.
Yeah, thank you for your presentation. I'm just kind of curious if you could say a little bit about in both the hydrologic model and maybe in the parts of EMOD that you've used, what the role of temperature is, and maybe how you see some of your results changing either if places get warmer, as they tend to, or just, you know, if you're using sort of a single daily value for temperature, as I often do when modeling with EMOD, what kind of limitations you see from that when maybe it's quite cool in the morning, warm at night, that kind of thing.
Yes. So for the hydrologic model, the temporal scale is actually hourly. So we input like hourly temperature data and rainfall data in our hydrologic model, and then the hydrologic model output the soil saturation. Then we can identify the habitats. So, and the temperature will affect the habitat area by like in the summer, like it might like evaporate faster. So I can comment on the hydrological model. I think the temporal scale is relevant. So in EMOD, it's like daily. So we have to aggregate our hydrological model output to daily, and then use like daily temperature and rainfall data in the EMOD. And I'm not really sure how the daily scale can affect EMOD model as well. Maybe there are other experts.
Thank you. Other questions? I see one up here.
Thanks so much for this talk. It was super interesting to see the hydrologic model combined with the dynamic model. I was curious, was there any malaria data from that area, like incidence or prevalence data, that you're able to compare with your model output to see how they lined up when you use similar irrigation practices?
Yes, for this model, we use 3 different types of malaria-related data. The first one is the adult mosquito density, and the second one is the prevalence rate, and the third one is EIR. But the data points are actually very few because we only have like few data for like 1 or 2 years. So we did do a calibration run for this area.
Thank you very much. We have time for a couple more questions. If anybody has one. I'll ask one, which is, I really appreciated this analysis as some incredibly detailed proof of what I think all of us anecdotally know, which is that so much of what leads to reduced malaria is changes in infrastructure, right? And changes in sort of the fundamentals of how people are living their lives. And I'd be really curious to hear more. You mentioned a bit at the end about how larval source management, for example, is integrating with this. But I would love to hear more about how your colleagues, or perhaps even the national program, are thinking really about this type of infrastructure change as larval source management, right? And how that might be affecting policy thoughts in Kenya. Thank you.
Yeah, we haven't really communicated our research with the local agencies, but I think that's the next step, move forward.
Incredible. All right, please find Eiling afterwards in the coffee break, and in the meantime, we'll move on to our final speaker for the day. Please, another round of applause.
Thank you so much.